All right, welcome everyone. All right, so I hope you enjoyed a lot of LM related presentations in the last 2 days. But now let's going back, take a break, take something relaxed, and going back to the traditional machine learning. This talk will spend 30 to 40 minutes about rethinking feature importance, especially SHAP values and TreeSHAP, specifically for tree-based machine learning models. All right, let's kick it off. So believe me, most of you here are machine learning engineers, data scientists, model developers, software developers, engineers related. A self-introduction for myself. I was in the finance industry for around 3 years, and my role is more like a model reviewer. So basically, after a model developer developed their models, we're going to review that. So we're going to evaluate, for example, if there's any limitations and assumptions embedded within the model and what risk we're going to pay attention to. All right, but as a role for data scientist, I believe every time you develop a machine learning models, your boss, senior managers, business stakeholders might be asking questions about what's inside that box, what's inside that black box. And for those people who doesn't really understand machine learning models, they probably view that as we take some input and the model is doing something inside, magical stuff. And then we're doing these predictions. But in this case, what you can explain to them are the local explanations as well as global explainability, which is the understandability for the entire model. And that's where the feature importance taking into the picture. So you can tell your audience which features are important, how much contributions each features are as like a positively correlated to your outputs or negatively correlated. And even for the feature engineers, you can select which features are important and which features you want to maybe exclude from your model. All right, so in this presentation, we're going to focus more on the global explainability. So we're not going to focus on specific data points, but in general, like which features are important for the entire machine learning model there. All right, so believing all of you are already familiar with SHAP, so this presentation could be refreshing of your knowledge if you already know of this. But believe me, like a lot of you are hearing SHAP every day. But I'm going to introduce a little bit on the origin of the SHAP, which is a game theory foundation, and explain the SHAP formula. And then we are going to walk through a simple SHAP example so we can do some simple math. Pretty simple. And then lastly, I'm going to introduce just SHAP assumptions from its original formula so you can have a better understanding on assumptions and limitations. All right, so what is SHAP? SHAP stands for Shapley Additive Explanations. It was originally introduced by Lloyd Shapley in 1953 as a method for fairly distributing gains in corporate game theory. It was adapted for machine learning model explainability by Lombard and Lee in 2017 to ensure a fair, consistent, and locally accurate explanations. So in the bottom side, we have the math equations. I'm not going to go deeply into that right now. I hope everyone is awake for some simple math calculations in the next slide. All right. So now it's a pretty cool example here. Who gets the credit? We have 3 minions. Anyone here not familiar with minions? Anyone here loves minions? All right. So we have Kevin, Bob, and Stuart, and they're going to work on this mission. And probably produce a final score of 14 bananas because they love bananas. So we're going to reward them with bananas. All right, so first we have what is called collation table here. So basically it's pretty simple. If none of them are working here, they'll get 0 bananas, 0 model output. But if only Kevin is working on this mission, he's going to get a score, what we call score or reward of 10. And then if Bob or Stuart is working singly on this mission, they're not going to produce anything because they're probably busy with their guitar mission or teddy bears. But if Kevin's the lead and he's going to work with Bob, let's say they're going to have a model output of 12. And if Kevin's the lead, they bring Stuart here, they're probably going to get a model output of 13. And lastly, if all of them are working together, they're going to contribute in the final score of 14. That's where the team set up here. All right, so now let's calculate how much bananas we should reward each of the mission here. All right, so we have the math equations. Not going to go deeply into that, but just to overall, so SHaP values is basically computing the marginal contributions for each feature, and then taking the weighted average for that feature there among all the subsets. Okay, so I'm going to put in the math equation directly so we don't have to do a lot of brainstorming and math working there. So for Kevin, basically recall that we're calculating the marginal contributions. So if there's nobody who's working on this project, the model output is going to be 0. But if Kevin is joining to this project, he's going to lead an upgrade to the model output to a 10. So basically the marginal contribution here is 10 minus 0. And then similarly, similar contributions here. If Kevin's joined with Bob, they're going to have the model output of 12. So basically 12 minus 0 is the marginal contribution for Kevin. And lastly, we have like Kevin working with Stuart, 13 minus 0. And lastly, we have Kevin join the existing contribution with Bob and Stuart. So that's lead to 14 minus 4. And then we take the weighted average. It's just fractional calculation dividends and sum them up. That's going to be 10.83. That's the bananas reward for Kevin. All right. Same calculations for Bob and Stuart. We apply the same mathematical formulas. It's pretty straightforward and simple. And then the Bob is getting 1.3 bananas and Stuart is getting 1.83 because he's contributing a little bit more. All right. So everyone's with me, right? Okay. All right, so now we have the basic calculations for origin SHaP for the game foundation theory. Now, what are the assumptions behind SHaP? Well, the first is we are assuming the feature is independent because we are assuming Kevin, Bob, like adding Bob to Kevin's team will not negatively lead to a decreasing contribution for Kevin himself. So we assume the features are independent when calculating marginal contributions, and the correlated features can distort Shapley values. And then similar features may split importance or double count effects. So that's potentially some negative aspect when the assumptions are violated for SHaP. The second assumptions here are the feature presence or absence simulation, which is SHaP basically calculates prediction difference by removing the features. So we assume the features can be simply masked out without breaking the model. But like think about the tree-based machine learning models. If we just mask out the feature, well, the tree still work. The tree structure is going to change completely differently, right? All right. So the last assumption here is additivity. So SHaP assumes an additive explanation model that exactly sums to the models being explained. So it's just kind of a little bit correlated to the first assumption there. So if we're adding Bob, and that's going to negatively affecting Kevin's contributions, then we can't just simply calculate the marginal contribution for Kevin by just minus 10 minus 0 or 10 minus 0, yeah. So these are the basic key assumptions behind SHaP. And actually in real world scenarios, most of the assumptions here does not hold. Because feature independence, in real world scenarios, a lot of features are actually highly correlated either positively or negatively. And as we mentioned, feature presence and absence does not hold for tree-based models. And lastly, additivity, some of them are non-linear, some of them are not just like adding them up. Okay, so the question came to, so SHaP gives a beautiful theoretical guarantee, but in practice, tree models don't always behave the way those assumptions expect. So can we compute Shapley values in a way that is both faithful to the underlying tree logic and faster than the model agnostic method? So here was the TreeSHAP came into the picture that we can explore a little bit and trying to identify if the limitations is mitigated through TreeSHAP. All right, so in the next sections, I'm going to introduce a little bit refreshing everyone's memory on tree-based models. I believe a lot of you are pretty expert on this field. But just to refreshing the tree structures, how does it work? And then I'm going to introduce the fundamental formula or the concept for TreeSHAP, how does it work? And lastly, I'm going to show a little bit case studies on real-world data I performed on 3 different data sets. The first one is HR, the second is finance, and the last one is social science. All right. So tree-based models, just take a simple and quick decision trees. We have like a tree leaves and splits and nodes. For example, here we're trying to predict the employee attrition, so whether employee is going to stay within the firm or leave the firm. And then we start with monthly income. If the monthly income is larger than a threshold, they're going to the right-hand side. a smaller left-hand side, and then following each structures and splits. And lastly, we have the predictions for the attrition. Random forest is just like a parallel, a lot of like independent decision trees, and then we're using, each of the tree here is independent, and we're using a bagging, which is a voting majority, as the final output for the random forest trees. CatBoost and XGBoost are a little bit more complex, and it's also pretty popular in today's world. XGBoost is just like the second tree is trying to optimize or mitigate the residual errors from the previous tree, and then following that structures until the tree is completely optimized and be the final results. CatBoost is using gradient boosting as well, but it's just like to prevent data leakage and also specific design for categorical variables. The sources are in the bottom, so you can find it pretty easy online for these diagrams. All right, so now let's introduce TreeSHAP. So TreeSHAP is still SHAP. It's still following the same logic here. So we're trying to predict the marginal contributions of each feature and trying to apply a weighted average for that marginal contribution. But it was designed specifically for tree-based models. So the model or the Shapley values can following exactly the internal structure of the trees for the splits and leaves, and then trying to calculate the exact SHAP values instead of they require sampling, because the standard SHAP requires sampling. If you do the calculations, it probably can take longer times, as well as taking some regression for the final calculation of the SHAP values. All right, so the core formula for the TreeSHAP here, it's basically just marginal contributions, but the marginal contribution here is the expected model prediction before the split versus after the split. So after the split, you can just calculate the probability, and then minus what was showing the expected model prediction before the split, and then times the weighted from the past P, which is basically just calculating by how many data points going through that path, how many data points going through this path. And then it's a probability, it's a fraction. It's pretty simple as well. And the additivity rule showing the second formula here, it's also the key function. It's also aligned with the standard SHAP. It's basically our features contribution exactly explains the prediction. So if we add them up, they will be exactly the final prediction score minus the expected final prediction score, which is the average. All right, pseudocode on the right, I'm not going to explain deeply into that because we have a pretty mature Python package and library you can call directly upon now. But it's just, yeah, something to show it here. All right, so let's go into some real-world data analysis. So I performed this small experiment on 3 different portions, 3 different industrial-related data set. The first one is HR workforce. The second is finance. And the third one is social science. All right, so each of the data set had their own different key takeaways and contributions and different characteristics. But let's dive into the HR workforce here. So I used the IBM dataset, employee attrition dataset, which was created by IBM data scientists. It was a synthetic dataset, but it's highly realistic, matching or trying to be realistic. The size here is not that quite large. It's 1,000 records with 36 features, so the features is quite large. And a lot of them are categorical features. A lot of them are high cardinality features as well. And the task here is to predict the employee attrition. It's a binary variable. It's basically whether the employee will leave the firm. It's a yes or no question here. So the features include are, for example, HR data such as department, job role, job level, but as well as demographic information such as age, gender, marital status, and lastly, the compensating information such as monthly income over time, working behavior, the total working years, etc. So on the right-hand side, we have this correlation matrix. So we can see a lot of features are actually a little bit highly correlated, is either positively correlated or negatively correlated. For example, the job level is highly correlated with monthly income. So if your job level, if you're a senior director, your monthly income is going to be high. Yeah. So I guess this data set is going to be really fun to test on for the first assumption there, which is high. The features are independent, but here we can see a lot of features are not independent. So these 2 slides are just to show you the plotting for all the categorical variables. So you can see some of them are only have 3 or 4 categories, but some of them are high cardinality, which is they have like a 10, more than 10 categories. So that could be a challenge as well. All right, so before we dive deeply into the SHaP values, let's just take a look on the permutation importance and gain importance first, because they're pretty popular and basic and classic importance method in academia, in industrial as well. So what we can see here is that for gain importance on the left-hand side, I fit a random forest model, by the way. So for gain importance on the left-hand side, we can say that like the top of the listed features, important features are actually tenure and compensating variables. For example, monthly income, total working years, years with current manager, they're all like tenure and compensation variables. And most of them are continuous variables. There is no categorical variables, but we have a lot of categorical variables. So what intuition from here is that the gain importance actually reflects how the model is structured, because it's listing the important features when they're like a reduced impurity early in the tree. And permutation importance on the right-hand side, we can see that it's actually matching more intuitively speaking, because over time, yes, job satisfaction, yes. So basically, if an employee is overly working overtime, they're probably gonna quit, leave the firm, right? And for the job satisfaction, if the employee is not satisfied with their job, they probably just leave the firm. And years with current manager, monthly income are still like highly important features there. So the key takeaway from here is that permutation importance is actually reflecting contribution to predictive accuracy, not just the tree structure, like the gain importance there. And comparison inside here is a different importance method, kind of focusing on different aspects of the model. So if you're trying to take a look on which features are important for impurity decrease or impurity early in the tree, you can take gain importance. But if you want to take more predictive accuracy that is matching more intuitively speaking, you focus more on the permutation importance. All right. So now there are the SHaP values, but just to go over my small experiment, I initially didn't do any balancing, like class balancing, because we have imbalancing target data. And for all the categorical variables, I did label encoding instead of the popular one-hot encoding. So, so without balancing and label encoding, here are the SHaP values in the TreeSHAP feature importance table. This is a B-swarm plot. I'm gonna focus on the B-swarm plot here. I know there are a lot of other SHaP plots they can produce, but I'm not gonna cover that in this presentation because of the time limits. All right, so what you can see here is clearly there are similar patterns actually in the top 4 features. It's actually semi important. Working overtime, age, stock option level, monthly income. But what we can see from the red dot here and blue dot, I hope everyone knows what red dot and blue dot is. So basically, if we have a bunch of red dot cluster on the right-hand side, it means the higher values for this feature is gonna lead to a higher probability, which is the predictive variable here is attrition risk. So what we can see here is if the employee is overly working overtime, yes, and then they're probably going to lead to higher attrition risk, so they're probably going to leave the firm. And some other findings here is like if the person is having like higher income. So if we see the monthly income, the 4 rows there, a lot of blue dots on the right, that means a higher income will lower attrition risk because all the red dots are clustered on the left-hand side. And similar for tenure information, shorter tenure increases attrition risk. So if people like to stay or change their jobs frequently, they're probably gonna increasing their attrition risk for the current job. And similarly for the satisfaction, so lower satisfaction increase attrition as well. So these are all matching intuitively speaking. So I would say it's actually performing okay, even without balancing and label encoding. So now let's take a look at after balancing and one-hot encoding, which is we can perform the model performance a little bit. Random forest models here as well. So we can see like some of the features are actually a little bit different from the previous without balancing and label encoding. But overall, the SHAP and TreeSHAP, it's actually performing similarly. It's actually having the similar outputs over time. Years with current manager, monthly income, total working years, all came to the top, and all 5, I would say top 6 features are the same, the importance. But what we can see here is that the clusters here, the SHAP, standard SHAP is a little bit unstable compared to TreeSHAP. So the cluster is more nested for the TreeSHAP especially. So basically the gain insight here is that, for example, gain importance is more focusing on model construction. Permutation is focused more on predictive accuracy. And then SHAP is more focusing on local contribution, but is sensitive to data issues, for example, imbalancing and a different encoding method. And TreeSHAP is generally more stable structure interpretability for tree ensembles. So I would say standard SHAP is actually doing okay here. So I would say, but standard SHAP will require careful preprocessing to avoid misleading results. And thinking about this is HR data. So sometimes we are trying to not predict anyone's information based on their gender, their age, their ethnic nationality. So especially for HR data, permutation importance is doesn't take that huge account for those features. So whenever we want to consider fairness considerations, permutation importance sometimes can be beneficial. And lastly, no-skill method is the best. We always want to combine methods. It's going to yield a deeper and safer insight. All right. So the next data set I'm going to test it on was the finance data set. It's a highly imbalanced data set. You can see from the right-hand side. I used Give Me Some Credit data set. It was released as part of the Kaggle Credit Scoring Challenge. It's containing 150K records with 11 features. So the task here is to predict if a borrower experiences serious financial delinquency within the next 2 years. And target variable is a binary variable, it's a classification as well. Features here is including, for example, the person's financial information such as number of opening credit lines, the real estate loans, revolving utilization, delinquency history, as well as some demographic information such as age, and also the composite information, monthly income, number of dependencies, etc. So what we can see from correlation matrix here is that a lot of them are highly correlated, even though we only have 11 features, but all of them are correlated. All right, so now I'm not gonna go for each of the small experiment. I'm just gonna listing all of the feature importance table here. So we have gain versus permutation versus SHAP and TreeSHAP. Here is a random forest model as well. So what we can see here is that for the permutation importance, it's actually listing the top listed features are all number of times, for example, 90 days late, of number of times, 60 to 89 days past due. So all of them are related to the historical delinquency records. But for standard SHAP and TreeSHAP, it's going to involving a combination of important features, like trying to understand this model a little bit more, a revolving utilization of unsecured lines, and the number of past due date, and then age, debt ratio, monthly income. So it's going to evolving a little bit more flavors into that model. But some obvious trend here is still for TreeSHAP, it's kind of involving a little bit more a clustering. So you can see more dots are clustered pretty obviously compared to standard SHAP. All right, and the last analysis here is the social science data set. So I took UCI adult income data set, which was collected from the 1994 US Census Bureau database. It's containing 48K records with 15 features. And the task is to classify whether a personal annual income is larger than 50K or less. It's still a target variable, it's a binary variable. And the features including, for example, education, occupation, demographic information such as marital status, age, sex, etc. But the key point here is that this data set contains a lot of categorical variables, and most of them are high cardinality variables. For example, occupation. What you can see from you probably can barely see it. But for the after one hot encoding, the occupation is increased dramatically because there are a lot of categories for occupation as well as native country. So they are considered high cardinality variables, and they're probably going to distribute the SHAP values if we do this one hot encoding. So that's one of the limitations for SHAP as well. All right, and now here is the results for the gain versus permutation versus SHAP and TreeSHAP, what we can see here is that the permutation importance is kind of matching a little bit more to the standard SHAP and TreeSHAP. We have the marital status on the very top feature there, which is surprising to see. But we have capital gain, age, education, hours per week, to strongly correlated with the target variable, which is whether a person's annual income is larger than the threshold. So similar patterns here. The standard SHAP is a little bit not that clustered than TreeSHAP. So TreeSHAP is considered a little bit more stable and nested for the clusters. And surprising to see that permutation importance, because we are taking a lot of demographic information here as well. So it's kind of similar to the HR data. It contains a lot of demographic information. So if we're trying to be fairness, if we're having that fairness considerations, the age here or the gender or the nation here is probably, we should not be counting that towards this model here. All right. So key takeaways. Basically, this is a table to compare kernel SHAP, which is standard SHAP, versus TreeSHAP. So just by the model type itself, the kernel SHAP works for any model, where the TreeSHAP is only designed specifically for tree-based models. And as for the computation, I probably mentioned that in the previous slides, standard SHAP is doing approximate. It's taking these samples every time and then apply a regression to form the final SHAP values for each feature. While TreeSHAP is just following the structures, the tree structures, and computing the exact SHAP values for the tree-based models. And it's going to be very fast. It's going to polynomial. Its big O here is T times L times D squared, which is the number of trees, and then the maximum leaves they have, and the maximum depths of the tree. But the kernel SHAP is going to be exponential. So during my experiment, the standard SHAP probably take 2 hours to run, and but the tree SHAP is take 5 minutes. All right. And for the stability across the runs, kernel SHAP can be varied because it's taking samples, and then we can be sure every sample it takes is going to be like a same. We have to set seed otherwise. Well, the tree SHAP is fully determinate because it's following the tree structures there. Okay, and now some key takeaways is that firstly, model interpretability isn't about finding one perfect method. Instead, we should be focusing more on the assumptions and limitations for each method. For example, gain importance, focus more on structures. Permutation, focus more on the actual predicting variables, and TreeSHAP and standard SHAP and TreeSHAP actually focusing more on a combination of them. And the second key takeaway here is that TreeSHAP generally demonstrate greater stability and consistency because it's computing exact feature values, SHAP values for each feature, and especially in an environment with highly correlated predictors and heterogeneous categorical variables, which is high cardinality variables. And also data cleaning and preprocessing were found to be critical for SHAP-based analysis. So any misleading data or encoding decisions can affect the attribution stability and interpretability validity. And lastly, permutation importance sometimes offer the complementary benefits. So especially for HR models, when we have fairness and sensitivity considerations that we don't want to involve gender, nationality, age into that factors, permutation importance sometimes can take a little bit benefit effects. All right, so that is all for today. Thanks everyone for joining. Any discussions, insights, questions?
Can I ask a question?
Yeah.
So I'm thinking about the second bullet point here, that so TreeSHAP demonstrates greater stability and consistency in cases where the predictors are correlated and the features are heterogeneous and categorical. So I think of the 3 examples you showed, the third one, is the third example kind of the best illustration?
Yes, exactly, because they have high cardinality features. But the CatBoost model, the third one, I fit the CatBoost model. So CatBoost model is able to, actually the tree-based model itself is able to handle those highly correlated predictors and mitigate the risk or the effects of SHAP over there.
So I guess what I was wondering is if you could rewind to the plots that showed the like the visualizations for that third data set. And I was wondering if you could, yeah, it's been a really long time since I thought about feature importance. Could you explain kind of like on 5, what the, like where you're sort of, you were talking about kind of the clustering and how the clustering illustrates stability. Could you just kind of walk through maybe one of these plots to sort of show, like here we can see more clustering and that tells us this, just to make sure I'm understanding it?
Sure, sure. So actually, what we can see here is that for each of the sample, for each of the feature here, TreeSHAP is actually having more like a clusters. For example, red dots on the right-hand side, education, non-marital status. Marital status on the first one here is actually pretty clear. Like they're having a lot of clusters here, and what you can see from the SHAP values at the bottom. So what does the SHAP values at the bottom means is basically and 1 point increasing in this data point in these features is going to increase in the predictive scores for that value, for that target variable. And then we can see a lot of like capital gains here. So standard SHAP, because it's using a sampling technique, so there's less points. So less points overlapping or nested into a left-hand side or right-hand side. But for TreeSHAP, we can see a lot of like clusters for, especially for age.
Got it. Okay, that makes sense. Yeah, and I see like for capital gain, it seems like it's particularly, you can see a much.
You can see an overlap because it's yes.
You can see a much stronger difference. Like on the bottom, the capital gain charts, there's like a big blob of like strong red on the right that you don't see as, it's not as pronounced on the top plot. So,
Yes,
okay,
yes.
Now I think I understand. Thank you.
Hello, yeah.
So for the formula for SHAP, could you go over it one more time?
The minions.
Yeah, just the one on the left part.
Yeah, so basically it's computing the marginal difference between each feature. So whether so if you see the correlation matrix, whether it's gonna involving these features, whether a subset is gonna involving these features minus the expected output for this involving that features. And then that's the marginal contribution part for player I. And then on the left-hand side, that's the weighted of subset S. So basically it's like how many components are within this subset. And we have like, for example, if we have 3 players in this game, so 3 times 2 times 1 divided by, I think 2 times 1 divided by 3 times 2 times 1, so that's lead to 1 over 3. So that's pretty simple calculation, so you just sum them up.
Thank you.
All right.
I have one question. So you said that TreeSHAP works better when the features are correlated as compared to SHAP. What are some scenarios where TreeSHAP would fail?
That's really a good question. Actually, I think most of the assumptions that is applied to standard SHAP is still applied to TreeSHAP. But the difference is the tree structure itself is gonna mitigate that risk. For example, if we have like highly correlated features, if they take that features as the first one and we take the split, the second similar features we're probably not gonna do a lot of split on that because they're highly correlated. So that's advantage for tree-based models itself. And then if the tree SHAP is following exactly the same tree structures, it will identify like how many splits are, and probably they will take less effect for that second correlated features. All right. Thanks everyone for joining.